Ooh, okay. Hey, buggers. Have you been bipping at people outside? Have you been going? Have you been talking to little doggos? What do you think about little doggos? Hmm? What do you think about little doggos? What about big doggos? Mm-hmm. What do you think? Who's that? Who's that? Who's that? It's people. Go get them. Go get them. All right. Good morning, everyone. I think I'm going to go ahead and... Oh, there he goes. He has a particular spot in the yard because I just have the back door open and the dogs and the cats are just going in and out all day. And dogs and the cat, I should say. And Bug likes to... He has a particular spot in the yard where he can see the sidewalk, he can see the road, and he hangs out there and he barks at anyone who walks by. So that's how he amuses himself. Okay, so I'm going to go ahead and get started on our lesson. So let's go ahead and review what we talked about last time. Okay, so last time we talked about the magnetic force. Okay. And so the formula for the magnetic force is, this is for the magnitude, is absolute value of Q times V times B times sine of theta. Okay, so when I say absolute value of Q, I mean if it's an electron, you make it, a positive charge. Okay. I'm sufficiently warmed up. So this is the amount of charge. This is the speed. This is the size of the magnetic field. What? What, Bug? And this is the angle between the velocity and the magnetic field. So, for example, if you had a situation where the velocity is pointed this way, and then the magnetic field is pointed this way as well, then that has theta equals 0 degrees. If you have a situation where the velocity and the magnetic field are pointed in opposite directions, that's a 180 degree angle between them. And if you have a situation where, maybe we got talking. Let's see. Bug, get her. Get her, Bug. Bug! Oh. Get her. Get her. Get her. Well, I thought they were going to play and I was going to catch it on camera. So if the velocity and the magnetic field are at right angles to each other like that, that would be 90 degrees, and so on. Okay? So we're going to talk about a number of things related to the magnetic force today. But one of the things I want to highlight is that this is the magnetic force on a single charged particle. Okay? So now let's talk about today's lesson, which is the first thing I want to talk about is the magnetic force on wires carrying current. Okay, so if you recall, electric current is the motion of charge. Okay, electric current is the motion of charge. So, excuse me. If you have a wire that's carrying current, okay, then that means that electric charge is flowing down the wire, which means that charge has velocity. Okay, so if a wire is carrying current, then that means that the wire has charge inside it with some velocity. Okay, so that means that there is going to be a force. So therefore, there will be a force on the wire. So I'm going to give you the formula for that force. So this is the formula for the force on a single charge. But if we have a wire with a lot of charge flowing down it, the formula is slightly different. So the magnetic force on a wire is, let's say, it is the current, the amount of current. So remember, current is measured in amps times the length of the wire. This is assuming that it is a straight wire. Okay, if you have a wire that's curved, you need to divide it up into segments that are approximately straight and apply this formula to each segment. B is the magnetic field, and then we have sine of theta. And so in the case of a single particle, the angle is the angle between the velocity and the magnetic field. But we can think about current as sort of the flow of charge, right? So it's so if you have a wire, this angle is the angle between the current and the magnetic field. Okay? So this is one of our formulas for today. So why don't we just do just a really quick example. Let's suppose that you know, a wire that is let's say a wire that is 11 meters long carries let's say 7 amps of current north, in the northward direction. There is a 2 Tesla west magnetic field. So we want to know, what is the force on that wire? Well, and remember, the tricky part about these magnetic force problems is the angle. Okay, so I recommend drawing it out. So we have the current is going north, so the current is going this way, and then the magnetic field is going west, which, north, south, east, west. So west is going to be that way. And so we can see that the angle between them is 90 degrees. So this tells me that theta is 90 degrees. And so then using F equals ILB sine of theta, I have 7 times the length is 11 times the magnetic field is 2 times sine of 90. And so the force on that wire would be, what, 154? I believe 154 newtons. Okay? So one of the things, so that's not really that much more difficult than for a single charge. So this is just an extension to that. What is a little bit trickier about magnetism is determining the direction of the magnetic force. So that's what we're going to talk about now. So determining the direction of the magnetic force. All right. So this part is a little bit tricky. So what we have to use is what's called so we're going to use the so-called right-hand rule, or possibly the left-hand rule. Okay, because we've talked about this formula gives us the size of the force, but force is a vector. It has a magnitude and it has a direction. So this is an equation for the magnitude of the magnetic force. This is an equation for the magnitude of a magnetic force. Okay, but how do we determine the direction of the magnetic force? And so we have to use something called the right-hand rule or the left-hand rule. Okay, and so the first step in the rule, okay, is you are going to use your right hand for positive charge or currents. Okay, so if it's a problem where it's a wire carrying current, you're going to use your right hand. If it's a proton, you're going to use your right hand. Okay, you are going to use your left hand for negative charge. So if it's something like an electron, moving in a magnetic field, you're going to use your left hand. Okay? So once you've done that, both your right hand and your left hand have pointer fingers. Okay? So you are going to put your pointer finger in the direction of the velocity. Okay? You are going to put your pointer finger in the direction of the velocity. Okay, like this. And then your middle finger does something different. So your middle finger is going to be in the direction of the magnetic field. By the way, I should say this is in the direction of the velocity or the current. I should have said that. So your pointer finger is the direction of motion of the charge. Your middle finger is the direction of the magnetic field. Okay? And then when you do that, your thumb sticks out. So you're kind of doing something like this. You're using these three fingers. You're doing one thing with your... It's going to make more sense once we do an example. But you're doing one finger with the velocity or the current, one finger with the magnetic field, and then there's your thumb. And your thumb is in the direction of the magnetic force. Okay? So this is the right hand rule or the left hand rule. Okay? You may have seen this if you are in an advanced math class and you've learned a lot about vectors. There's something called the cross product. And so this is basically what we're doing is we're learning how to determine the direction of the cross product. So this shows up this kind of rule shows up anytime you have a cross product. So let's do some examples. So these examples are going to be of the form a blank travels blank in a blank magnetic field. And we want to know what is the direction of the force. So we're going to do a lot of examples. So let's suppose we have a proton travels north in an upward magnetic field. So what is the direction of the force in that case? So what you want to do for these problems is you want to draw a compass rose. Okay, so I have north, south, west, east, and then furthermore, we have so magnetic field problems are inherently three-dimensional. Okay, so we are going to have into the page is down. Okay, so I'm putting an X to represent the direction that is into the page. Why is that? If you can imagine firing an arrow, and as that arrow goes away from you, you're going to see the feathers on the back of the arrow. So this is like the feathers on the back of the arrow going away from you. So this represents down, which is into the page, right? Because an arrow would be going away from you down. Up is going to be represented by a dot. So that is the direction that is directly towards the camera. And the dot is representing the tip of the arrow headed straight towards you. Okay? So let's apply the right-hand rule. So we have a proton. So saying that it is a proton means I'm going to use my right hand. Now I think, I'm not sure if my camera is reversed or what, but this is my right hand, okay? And it's traveling north. So that means I'm going to put my pointer finger in the northward direction in an upward magnetic field. So what I need to do is I need to point my middle finger upward. All right? So I'm keeping my pointer finger going north, but I am going to rotate my hand so that, see how my middle finger is pointed up towards the camera. So see my compass rose right here, okay? And then I can see my thumb is going off to the side here, which the direction of my thumb is the eastward direction, okay? So that means that the force would point in the eastward direction, okay? So now let's do another example, and then this is getting a little crowded, so I'm going to flip the page over after this example. Let's suppose we have an electron traveling suppose we have an electron traveling west in a northeast magnetic field. Okay, so because it is an electron, I'm going to use my left hand now because electrons are negative charge. So it's traveling west. So I'm going to put my pointer finger in the westward direction. All right. So there's my pointer finger in the westward direction. And so now I got to point my middle finger in the northeast direction. All right. So I can't do that. I can't point. See how the northeast direction is that way. I can't point. So you have to kind of rotate your hand until you get it into the right orientation, which is going to be really tough to do. Here, I better. Do you mind if I rotate my piece of paper here? Just to make this easier on me. So here I have my pointer finger going west, and now I have my, see how I have my middle finger is pointed northeast according to this system, right? Northeast is in that direction. Okay? And I can see that my thumb, when I do that, my thumb is up towards the camera. So that means that the direction of the force is out of the page, which is up, in the up direction. Okay? Let's do some more, because this is tricky. So the format of our examples is a blank moves in the blank direction in a blank magnetic field. Okay, and we want to know what is the direction of the force. Okay, so let's suppose we have a current. Oh, and I'm going to draw my compass rose here just so that we can north, south, west, east. Down is into the page, up is out of the page. Let's say a current moves downward in a northwest magnetic field. The current moves down in a northwest magnetic field. So what is going to be the direction of the magnetic force? So it's a current. So for the right hand rule, I use my right hand for the current. Okay. And I want to point my pointer finger in the direction of the direction of that current flow, which is downward into the page. Boom. Okay. So I got my pointer finger going down. Then my middle finger is under here. Hello, middle finger. I'm going to point that in the northwest direction. So I'm going to even stand up just to make this easier on myself. So now my middle finger is pointed in the northwest direction. Can you see that? Here, and then here is northwest. So that works. And then I can see my thumb is pointed in this direction, which is northeast. So the direction of the force would be in the northeast direction. Okay? So there you have it. What if we have an electron travels, let's say, north in an up-north magnetic field? Here's another example. Okay. So what do I mean by up north? Well, I was thinking about, we have northwest, we have northeast, we have southwest, we have southeast. Why can't we have up north? Right? Northwest is halfway between north and west. Up north is halfway between north and up. So it's kind of like in a direction that's diagonally, not straight up, not this way, but halfway between. So it's a diagonal direction, kind of like that. Okay. So that's what I mean by up north. So I use terms like that. I'll say down north, or I'll say up east. Up east let's suppose we have up west. What if we had up west? Up west would be kind of not up, not west, but halfway in between. So, anyways, let's go back to the example. So I have an electron, so I use my left hand. The electron is traveling north. So I put my pointer finger in the northward direction, and then my middle finger is in the direction of the magnetic field, which is up north. Okay, so you have to basically rotate your hand so that it's in an orientation where the middle finger can point in the direction it needs to go in. So it's kind of like this. This would be my finger pointed up. This is my finger pointed up north. Okay, and I can see that my thumb is extending off to the left, which is in the westward direction. So this is a westward force. Let's do a couple more. What if we have a neutron instead that is traveling north in an up-north field? These are the kinds of ones where you got to be careful, okay? Because this is a neutron, okay? Neutrons have no electric charge, okay? No electric charge means that the force is zero, because it's QVB sine theta. So if Q is zero, then there's just no force, okay? What if we had a proton that is at rest in an up-north magnetic field. So neutron means that the charge is 0. At rest means that the velocity, the speed, is 0. Okay, and as we see, the formula for magnetic force, QV B sine theta. So V is 0. Okay, so that means that the force is going to be 0. Okay. What if we have an electron travels what if we have an electron that travels, let's say, northeast in a southwest magnetic field? Okay. An electron travels southeast in a southwest magnetic field. Well, let's just draw that out for a second. Okay. Northeast is this direction, so that's the direction of the velocity. Okay. The magnetic field is southwest, so I can see that based on this, the angle is 180 degrees. Okay. So, and then the sine of 180 degrees is 0. So if we look at our formula, QVB sine theta is 0. Okay, so that makes the force 0. So you should be aware of these special cases where Fmag is 0. Okay, so the things that can cause the magnetic force to be 0 is if you have 0 charge, if you're at rest, or if the velocity and the magnetic field are either parallel or anti-parallel. Okay, so let's do one more. And okay, so we have let's suppose we have an electron is traveling let's say east in a let's say in a down south magnetic field. Okay, so I'm choosing my hands. First I have to choose which hand I'm going to use. An electron has negative charge, so I'm going to use my left hand. Okay, then I'm going to put my pointer finger in the direction of the velocity, which in this case is the eastward direction. So I'm pointing my pointer finger towards the left. Okay, now I have to take my middle finger and point while keeping my pointer finger going in the eastward direction. I have to rotate that so that my middle finger is pointed in the down south direction. So with my hand in this orientation, it would be south. With my hand in this orientation, my middle finger is pointed down. So down south is like halfway in between, so it's like this. Okay? And so I can see that my thumb is not pointed up, it's not pointed south, it's pointed halfway in between up and south, which is the up-south direction. Okay? So that is how the direction of the magnetic force works. Okay? And it should not be confused with how the direction of the electric force works. Okay? Suppose we shifted the example and we said a blank moves blank in a blank electric field. So the way electric fields work is that positive charge is pushed along the field regardless of the velocity. Okay? So for example, if we have a proton moves north in a southwest electric field, well, a proton is a positive charge and the electric field is southwest. Regardless of the direction that the proton is actually headed in, it's going to get pushed and turn in the southwest direction. So the direction of the force is southwest. Okay? If you have an electron traveling, let's say, east in an eastward electric field, so an electron is a negative charge, which, regardless of its direction of travel, so this doesn't even matter. The direction of the velocity does not even matter if we're talking about electric fields. Okay. Negative charge gets pushed against the electric field. So what is the opposite direction of east? It is west. Okay. So I'm going to put here, be aware of the differences between electric and magnetic forces. Okay. So we have one more thing to talk about. So we got a fairly packed lesson today. And so the topic of this last part is called the cyclotron radius. Cyclotron radius. Okay. One of the things you want to notice about the magnetic force, so let's say note, is that when you're doing the right-hand rule, your pointer finger is in the direction of the velocity and your thumb is in the direction of the force. Okay? And unless you have a particularly disfigured hand, I'll put it this way, the ideal hand has a 90-degree angle between pointer finger and thumb. Okay? So what that means, and because the thumb represents velocity and the pointer finger, because the pointer finger represents velocity and the thumb represents force, that means that the force, or the velocity, is perpendicular to the magnetic force. Okay? Now, according to net force equals ma, Newton's second law, we can see that if the force is in one direction, okay, then the acceleration is also going to point in that direction. So that means that the force is in the same direction as the acceleration. So the velocity is also going to be perpendicular to the acceleration. Now, if you remember, there was a certain situation where we had the velocity and the acceleration were perpendicular to each other, and that was circular motion. Okay, so for circular motion, we had the velocity was tangent to the circle and the acceleration was in towards the center. Okay, so basically the magnetic force causes circular motion. The magnetic force causes circular motion. Okay. In fact, and this is a really important point, in fact, the magnetic force cannot change the speed of a particle. This is an important point. Okay, so I'm going to put it in a box. The magnetic force cannot change the speed of a particle. Why? Because you have to apply a force that's in the direction of the velocity to change the speed. Okay, so what the magnetic force does is it deflects. So the magnetic force can take something that's going 5 meters per second and it can turn it so that it's going 5 meters per second in a different direction. But it can't make it go from 5 meters per second to 6 meters per second. Okay? So all it can do is turn particles. It can't change their speed. Okay? Let's suppose we have a particle that is headed this way, and it enters a region with a magnetic field that is, and let's say this is a positive charge, okay, with a magnetic field that is going in to the page. So there's a magnetic field going in to the page. So I'm representing that with X's. So this is the magnetic field. So let's determine the direction of the magnetic force as it enters this region. Okay, so I have I'm going to move myself so I can do this more easily. It's a positive charge, so I'm using my right hand. I have a velocity that's going, okay, I have a velocity that's going to the right, and I have a magnetic field that's going into the page, so I'm going to take my finger and point it down into the page, and you can see that my thumb is going upward towards the top of the page. Okay, so when it enters this magnetic field, it's going to have a force on it that's going up towards the top of the page, which means that when it enters, it's going to curve in a circle like this. Okay, and in fact, it's going to do a perfect circle, and then it's going to leave in the same direction that it came from, so it's going to go back in that direction. Why? Why wouldn't it just keep moving in a circle? Because once it gets to the top of the circle, it then would exit the region with the magnetic field. So now that there's no more magnetic field, it just keeps going straight. All right. So we would like to figure out, how do we determine the radius of this circle? That is called the cyclotron radius. Cyclotron radius. Okay. And so it's really quite simple. So we're going to have net force equals ma. Because the particle is moving in a circle, the formula for acceleration is going to be the centripetal acceleration, v squared over r. Okay. And we are going to assume, just like in this example, that the angle between the velocity and the magnetic field is 90 degrees. Okay. And the sine of 90 degrees is 1. Okay. So if we take our formula for the magnetic force and we have sine of theta equals 1, then our force is just QVB. All right. So the only force acting on the particle in this example is the magnetic force. So our net force is QVB. And so I can see that the V cancels out one of the factors of V on the right-hand side. So I have QB equals mv over r. And I can solve for r. I get r equals mv over qb, absolute value of qb. So this is called the cyclotron radius. And it is a handy-dandy thing to know about. Okay? So that is my lesson for today, and I will see you in the Zoom room.